what is motion and how can we conceptually describe motion? I'm not going to reread the section to you, but I do just want to point out a couple before I get into the homework answers. A couple of important things. Well, first being is this is our first real homework video. Make sure that as you read the section, there's not a sentence in it that you don't understand. If there is a sentence that you don't understand, you've got to email me. And once we get into the school year, you got to write it down on a paper so you know to ask me the next day. We don't do extra school help in that you don't wait until 2:30. You've got to, in the course of the 80-minute block, say, I don't get that right now. Tell me what it means. And then my job is to try to get you to stop asking so many questions so I can get through all the material. And then we just got to find that in between where it all works out. So you've got to make sure if you don't understand something, you say. What you're going to notice here is I'm not going through this entire section. As we get through the course, you won't always see me doing what I'm doing right now, which is I'm about to describe a little bit of what goes on. You've got to be responsible on your own for knowing what you don't know. It's really important. You got to know what you don't know, and then you ask. You got to get it answered. Why? I don't quite understand this. Why is it happening this way? But this is really important. Weaker students will come to me and say, will you do one of those density problems? Well, that just tells me that they haven't even really tried. They're completely lost and they just want me to tell them what to do. You've got to be able to say, I don't understand how to Sifu that density formula for mass when I'm given density and volume. What is it that I'm supposed to do here? So you got to know exactly what it is that you don't know. It's Sifuing, it's not really the density formula. So you figure that out by when you're reading these sections in the book. When you go across a sentence or a concept and you don't understand it, you got to ask. All right, into the chapter. Really interesting little thing there. Tim sees the basketball moving. Jan sees the basketball as always being at rest in her hands. And it gets into that concept of a frame of reference where you got to know, are you basing this on Tim's observations or are you observing it on Jan's observations? Because again, one person sees the position of the basketball changing, the other one sees it as being at rest. So once you do that, the coordinate system's kind of easy. We do these in all the problems we solve, but you got to know basically x, y. We rarely do three-dimension. Basically, you got to have an x and a y, a left and a right, an up and a down, etc. And you won't have a problem with that. The frame of reference sometimes tricks you, but the coordinate system and obviously the clock don't bother you so much. And then look, there was a definition of linear motion is a model. Yeah, that's a word that came out of that previous introductory chapter, right? Of motion that assumes that an object considered a point-like object moves along a straight line. So again, we're not going to really give volume to that basketball. It's just a point in space that is moving relative to Tim, not moving relative to Jan. So those are some definitions quickly from the section. The second section, now this is the big one that you've got to know, and you're going to use this throughout the course, and that is drawing these motion diagrams. So you draw a dot to represent the position of the object at equal time intervals. That equal time intervals becomes quite important because we're going to want to make sure that I'm going to skip ahead to something we haven't talked about yet, constant speed versus increasing speed, and I can tell that because it's traveling a greater distance. And I'm using a definition we haven't come up with, but I'm pretty sure you're comfortable with speed as distance over time. So in a motion diagram, we draw dots at equal time intervals, and you can't miss that, how important it is that it's got to be at equal time intervals. And then you point a velocity arrow in the direction of motion with relative lengths to indicate approximately how fast the object's moving. Slow, fast. Slow in the opposite direction, fast in the opposite direction. So those arrows are really important in a motion diagram. And then draw a velocity change arrow to indicate how the arrows change. So here I might draw, these are arrows getting bigger, sorry, new smartboard that I'm getting used to here drawing on. So that motion diagram on the bottom is showing an object that is going faster and faster, and then its change in velocity is also in that same direction. Whereas if you take an object that is moving fast and slows down in equal time intervals, so these dots should be getting closer together. I don't know how good a job I'm doing with that. Right here, this arrow is moving to the right, and this will trick you here a little bit in the beginning, but the change in velocity arrow, we say, is to the left. So there was a little definition given in the book about the change in velocity, and then they put this little arrowhead above it because there is direction associated with it, and it's the final velocity minus the initial velocity. And this is how Regents kids would, somewhat how Regents kids would write it, so I'll simplify it to that right now. So the change in velocity is just the final minus the initial, and if something slows down where the final is slower than the initial, the change in velocity direction just comes out in the opposite. I hope my grammar was okay with that. Okay, so let's look at these problems. The car starts from rest, so I put a dot, and then it speeds up. So I'll make these dots get farther apart as it speeds up, and I will draw arrows getting progressively larger as it goes faster and faster. It then moves at a constant speed. I certainly didn't save myself a lot of room here. Then I want to show dots. So I moved it for you. Now we got to go at a constant speed. So I will keep the dots at a constant. Let me just make them smaller dots, please. Okay, so now I'm going to have the dots be a constant distance apart. I hope that's showing decently. And then what do you do? Slows down, right? Then it slows down until reaching the next stoplight. So now I got to make the dots get closer together again. So I should have arrows here in the middle that are the same length. Please tell me those 4 arrows are the same length. And then I'm going to have them get progressively smaller again until it stops at the end. If I were to do a delta V in the beginning, it would be to the right as it speeds up. In the middle, delta V would be 0 because the speed doesn't change. And at the end, delta V would be in the opposite direction that it's moving because it slows down. So there's number 1. There is your motion diagram for the car starting at rest, hitting constant speed, and then slowing down. And here is a cleaner version of the same thing with arrows more clearly defined with their lengths. Number 2, you're an observer on the ground. Draw 2 motion diagrams representing the motions of 2 runners moving at the same constant speeds in opposite directions towards you. Runner 1's coming from the east, reaches you in 5 seconds. Runner 2 reaches you in 3 seconds. So I will just put a little picture of the person, and then we have one individual running in one direction at a constant speed towards you. So I'll try to do same size arrows, equally spaced, and label those all V. And then the other one is same constant speed but runs longer. I should have those dots be the same distance apart as the previous part, but put the arrows in the opposite direction. So I drew the observer in each case, and then I have arrows going toward, arrows going toward you from, let's say, the east or in one direction, and then arrows going towards you but coming from the opposite direction, and I show the speeds are the same. B, draw a motion diagram for the second runner as seen by the first runner. Well, they're both running at the same speed. Now this is where things start getting a little tricky. They're both running at the same speed, but if you take from the frame of reference of one runner, the other runner running towards him, he will see that runner as going twice as fast. So I want to show a diagram that in those time intervals, the speed is twice as great. So same distance between dots, but same time interval, but twice the speed for one runner compared to the other. And I think I want to, All right, erase that for you. There you go. So that would be the Part B motion diagram, where one runner sees the other runner coming towards him, but with twice the speed as the observer on the ground would have. A little tricky. Okay, for number 3, a car is moving at a constant speed on the highway. A second car catches up and passes the first car, and it starts to speed up. A second car catches up and passes the first car 5 seconds after it starts to speed up. And so let's draw a motion diagram. And here is the kind of problem that beginning students hate. Like, what do I use as my frame of reference? I'm going to use the ground, the earth, because I know, and it's easier to do this than it is to draw the frame of reference from one car to the other. So what I'm going to do is say that dotted line is where the cars are going to catch up to each other, and then I have the first car moving along at a certain speed as it goes towards that line, and that observer has a constant speed, so it's got a delta V of 0. That object has a constant speed, so it has a delta V of 0. And that should be over 5 seconds, so I think I missed a dot, and all of those are the same length. Now the second car is going to start behind the first car, so I'll come over here and make my 1, 2, 3, 4, 5 dots where the arrows should be getting longer because that car was speeding up over those 5 seconds with a change in velocity in the same direction that the car was moving. Now those dots in red should be the same spacing, and I didn't do a great job of that. They should be the same spacing as the dots in black were, just that the arrows are getting farther apart. The arrows are getting longer for the second car that is speeding up. But the distance between dots is, in a motion diagram, a time interval. So the time interval that I'm counting should be the same for both the black object and the red object. So this one does it, machine done. This one does it a little bit better. You can see the top set of arrows for car 1 are all the same length because car 1's speed doesn't change, but car 2's speed does change, so car 2's arrows are getting longer and longer. And again, the dotted line is just where they eventually pass one another. Motion diagram showing car 1 going at a constant speed, car 2 speeding up, going in the same direction. And a hat falls off a man's head. Draw the motion diagram as seen by the man. So he will see a hat start at rest, and then here, I'm going to do this one better. Equal time intervals, so those dots are every second, and you're going to get confused later when we show where an object is. This is just showing equal time intervals right now, and I want to show that the man's hat speeds up. I'll end it like that. So here I've got, 1, 2, 3, 4, 5 dots with arrows getting progressively longer because the hat is speeding up in the downward direction as it falls off the man's head. And I'll just label this something like, here's something that we'll do as we get into the course. We'll label these speeds at different points, 3 and 4. So 4, 3, 2, 1, 0. So yay, doesn't that look good? And really one cool thing that I like is that we call that naught. So we would label those speeds V naught, V1, V2, V3, V4, and you'll find that a cool word that we get to use here in AP. So motion diagram, hat from the perspective of the man's head. These motion diagrams will become really important to you as we go through these words. Distance or position and speed or velocity. One's a scalar, one's a vector. Acceleration. So we're going to start to describe the motion of an object over the rest of this chapter and the next couple of chapters when you get into school with me. And we're going to be able to describe things based on a motion diagram. So these motion diagrams are something used by your author an awful lot, and they have been appearing on AP exams, so they're worth understanding. And they are simply, once you get used to them, right now in the beginning, you might be freaking out like, oh, I don't know if I'm doing these right. Oh my gosh. You'll get better at them. You'll start to recognize, really just draw an arrow in the direction it's moving, and the length of the arrow represents speed. And this little bit right here, which is tied to the acceleration when we get to it, the direction of the change in velocity, when something slows down, it's in the opposite direction of the direction it's moving. That'll confuse you for a little while, but then you'll get used to it. So motion diagrams, thank you.